Here we have a picture of a wheel whose mass is 4 kilograms, but it's got a bunch of 8 kilogram spokes. Each spoke goes from the center out to the rim of the wheel and has a mass of 8 kilograms and a length of 0.4 meters. The radius of the circle is, of course, 0.4 meters. And we want to calculate the moment of inertia of this system, where we have 8 such spokes and one rim of 4 kilograms. The moment of inertia is the sum of all the mr squareds, and for the rim, the 4 kilograms out at the rim, that mass is all right at approximately the 0.4 meter distance. We're going to have mr squared is 4 kilograms times the square of 0.4 meters. And then we're going to add 8 times the moment of inertia of a spoke. Now what's the moment of inertia of this spoke? Well, that spoke is really a rod or a beam that's 4/10 of a meter long, rotating about one end with a mass of 8 kilograms. Then we assume, I think it's stated, that this is a uniform spoke here, so that we can use the yeah, that's right, never mind. We use the 1/3 ml squared to get the moment of inertia of each spoke and multiply that by 8, add it to this, and we get approximately a total of 4 kilogram meters squared. And you can check those, you can and should check those figures. Now, if we apply a torque by applying a 25 Newton force to this wheel at the rim, then the torque of that force will be 25 newtons times the distance from the center, 0.4 meters. It's stated that the torque is applied at the most advantageous angle, which of course will be tangent to the circle formed by the rim. If the torque is applied, or the force is applied here, it'll be out in this direction, tangent to the rim, and we get a torque of 10 meter newtons. Then we calculate the acceleration of the system, and that acceleration is just torque over moment of inertia. Very straightforward calculation, gives us negative 2.5 radians per second squared. We're asked how long it'll take this thing to accelerate at this rate through actually the torque that we're applying is going to give us a negative acceleration. We're going to slow the thing down from 10 revolutions per second to 0 with this acceleration. So how long is it going to take that 25 Newton force with the 10 meter Newton torque to stop this thing from 10 revolutions per second? Well, 10 revolutions per second is 62.8 radians per second, and we're slowing down from that speed to 0, so the change in angular velocity is negative 62.8 radians per second. At a rate of negative 2.5 radians per second squared gives us a delta t that's equal to the delta omega divided by the alpha. And we can easily calculate that result.